Hi, I'm Eva Murphy from Electronic Engineering at IT Sligo, and this is my Leaving Cert Maths Grinds channel. I'll regularly add new videos for both higher and ordinary level maths, so make sure you subscribe below and click the bell icon to be notified of new videos. Okay, so from the 2014 sample paper, W equals 1 plus root 3i is a complex number where I squared is equal to minus 1. Write W in polar form. Okay, and you can see it's plotted for us, minus 1 plus 3i, plus root 3i. Okay, so we've done a few of these. To write it in polar form, we need to figure out the modulus, which is basically means what distance is it from the origin. Okay, so what's that length? What's that length there? Okay, and to do that, we form a triangle basically is what you're doing, and you're using Pythagoras Theorem. So r is equal to the square root of 1 squared plus root 3 squared. You come over 1 on your x-axis and you go up, or you come over minus 1, same thing, and you go up root 3. Okay, so put that into the calculator and you get r being equal to root 1 plus 3, which is root 4, so r is equal to 2. So that is a distance 2 out from the origin. Right, let's have a look at our angle. My angle theta is that one. We always start from the positive sense of the x-axis. But first I need to work out my reference angle, okay? So my reference angle is equal to, let me do it, the tan of that reference angle, let me call it theta, is equal to opposite over adjacent, which is root 3 over 1. Okay, so the two formulas, if a complex number is x plus yi, your tan is y over x, so it'll be this number over your real number, and r is the square root of x squared plus y squared. Okay, they're the two formulas you need for polar form. So therefore theta, the reference angle, is the tan inverse of root 3. Where's my calculator? You can do it in degrees, you can do it in radians, it doesn't really matter. Tan inverse of root 3, and I must be in degrees. I'll just check now. Well, I must be with that angle. And let me change to radians. Or you could have the tan inverse of root 3 being a third pi. Okay, and then when you're in quadrant 2, what you do is you subtract your reference angle, this little bit here, from the full 180 degrees that's across there. So therefore, I shouldn't have called it theta, is equal to 180 degrees minus 60 degrees, so it's 120 degrees. So in polar form, W is equal to 2 times cos 120 degrees plus I sine 120 degrees. Okay, of course I could have done pi minus a third pi to give me 2/3 pi as your angle if you're doing it in polar form. Okay, so remember that in the log tables, which way is Demarva's theorem? It's just a little, or polar form, it's just a little bit hidden in Demarva's theorem. There's your r cos theta plus I sine theta in case you forget it. Okay, very important to be able to write in polar form. Okay, and what I would expect to come normally after that in a question is some use of Demarva's theorem, because to be able to use Demarva's theorem, your first task is to write it in polar form. Okay, so use Demarva's theorem to solve the equation z squared is equal to minus 1 plus root 3i. Okay, so we're going to solve it for z basically. So they're giving us z squared and we're going to solve it for z. So minus 1 plus root 3i was 2 cos 120 degrees plus I sine 120 degrees. Okay, so therefore z squared is equal to 2 cos 120 degrees plus I sine 120 degrees squared. Okay, and we'd like to know what z is. Okay, so how do we go from z squared back to z? Well, using the rules of indices, if I multiply that by a half, in other words, if I raise the whole thing to a power of a half, then 2 times a half is 1. Okay, but to do that, then I would have to change this dude to, I knew it didn't look right, there's my squared. I would have to raise this one to the power of a half. Okay, so that's 2 cos 120 degrees plus I sine 120 degrees, which is this, to the power of a half. Okay, so applying Demarva's theorem then, Demarva's theorem tells you that when you have a power, raise or to that power and multiply your angle by that power. Okay, so what does that do here? Well, it's 2 risen to the power cos a half times my angle plus I sine a half times my angle. Okay, and actually if I'm going to do it perfectly by the book, I'm going to do something first. I'm going to write it in general form so that I apply the half to the general form too. Okay, so 2 to the power of a half cos half my angle. So it's the same thing. I just want to make sure that the general bit also gets halved. Okay, that's important, that you're not adding on in 360 degrees after you have applied Demarva's theorem. So 2 to the power of a half then is root 2 cos 60 degrees plus n 180 degrees plus I sine 60 degrees plus n 180 degrees is what you should have at this stage. Okay, so I'm just going to go onto a new slide. Okay, so what you do then to find your roots is you let n equal to 0 to find your first root. So you'll have root 2 cos 60 degrees plus I sine 60 degrees. Okay, so what happened there? Well, n was 0, so this whole thing goes to 0. So cos 60 degrees plus I sine 60 degrees will give you your first root. Now the question says to give your answer back in rectangular form, so you need to multiply this in. So let me put that in my calculator. So root 2 cos 60 degrees gives me root 2 over 2. Okay, which, by the way, is the same as 1 over root 2. Okay, and I'll explain why that is in a minute. Plus, and I'm going back on my calculator to delete cos and put in the sine. Root 6 over 2. Okay, so that's the first one. Why is root 2 over 2 the same as 1 over root 2? Well, they're writing this as root 2. One of them cancels and it's 1 over root 2. This to me is the normal way of writing it. I have no idea why your calculator gives it to you, or definitely the Casio calculator gives it to you as root 2 over 2. Whatever way it's programmed, that's how it does it. So that's one of your roots. The second root comes from when n is equal to 1. So root 2 cos of 60 degrees plus n is now 1. So I'm going to add on 180 degrees plus I sine 60 degrees plus 180 degrees again. Okay, and you can do this all in one go if you want, or of course you can write it out for yourself. Let's put that into a calculator, root 2 cos 240. And in this case, I get minus root 2 over 2 plus, let me go back and change cos to sine, minus root 6 over 2. Okay, so they are your two roots. I want to make one point about roots before I move on. Okay, so when I look at them, they feel right, and I'll explain why. So if you draw your, do they have this plotted for me? No. Okay. So if we plot these, okay, and I'm not even too fussy about the actual numbers. I'm more interested in the quadrants and their location. So this is over root 2 over 2 and up root 6 over 2. Okay, and then this one, if you look at it, it goes the opposite direction. It goes minus over about the same amount and down about the same amount. Okay, so somewhere there, which is exactly what I expect, because the roots of a complex number will always form a circle about the origin, okay? And they will always be an exact number of degrees away. So in other words, if you have two roots, they will be 180 degrees apart. If you have three roots, you might have one here, and one down here. In other words, they'll be 120 degrees apart. So it's 360 divided by the three roots. Okay, they'll be 120 degrees apart. Obviously, then if you have four roots, your roots are going to be 90 degrees apart. Okay, so something like that. And they can be at different angles. Okay, but they will be 90 degrees apart. So look out for that when you find roots of complex numbers. They do form a pattern. Okay, four complex numbers, Z1, Z2, Z3 and Z4 are shown on the arcane diagram. They satisfy the following conditions. Z2 is equal to I times Z1. Z3 is equal to K times Z1. Z4 is equal to Z2 plus Z3. Okay, so the first one there, just pull up a book because there's a specific page that I just want to go through with you, and over Zoom is fine because I can explain it with a diagram. Okay, so the book I'm looking at here that I think does it the best, this particular section, is the Project Maths book. Okay, okay, so if you have that, it's really good. Right, so the first few things that you need to know about, I suppose, the geometrical properties of complex numbers. Okay, the first thing is what does I do to a complex number? Okay, so if you have a complex number Z equal to 2 plus 3i, when you multiply it by I, you'll get 2i plus 3i squared. He's going to become minus 3. So you'll end up with, if we write the real part first, minus 3 plus 2i. Okay, and if I was to plot these, what you'll end up finding is that Z and IZ are 90 degrees apart. Okay, so in other words, 2 plus 3i is somewhere here, and minus 3, I come over another bit and not up quite as much, is 90 degrees apart. Now, what do I mean by 90 degrees? Now, these aren't accurate, okay, but there is Z, and it's 90 degrees here about the origin. That's IZ, okay? So there is your 90-degree angle between the two. And it is always anti-clockwise, always, always, always. Okay, so the relationship between a complex number Z and IZ is a 90-degree rotation anti-clockwise. In the same way, if you multiply a complex number by I squared, well, I squared is -1, so it's actually going to change the sign of the two of them. So you're going to end up being down here, okay? So what it is an anti-clockwise rotation of 180 degrees, okay? So I hope you're seeing the pattern now. I cubed an anti-clockwise rotation of 270 degrees, okay? Or sometimes you see that one being described as a clockwise rotation of 90 degrees, okay? But really, strictly speaking, it's a rotation, an anti-clockwise of 270 degrees, okay? I to the power of 4, you end up back in the same part. I to the power of 5, you're here. So you just keep going around in the same places all the time. So that is really important. What happens when you multiply by I squared, I cubed, and so on and so forth. Okay, so that's the first one. The second one is when you multiply it by k. Okay, so this is called a dilation. So what you're either doing is stretching out or enlarging the complex number, or you are shrinking it, basically. Okay, you're making it smaller. So in other words, if k is less than 1, the complex number gets smaller. Okay, so the complex number gets smaller, or in other words, it moves in towards the origin. Okay, so as an example, if I have 4 plus 2i and I multiply it by 1/2, then I get 2 plus I. Okay, so you can see one that's out here at 4 plus 2i ends up going at half the way in. Okay, so it's a dilation. And obviously then if it's greater than 1, it ends up pushing it out further. Okay, so again, that number 4 plus 2i, if I multiply that by 2, 2 4s are 8 plus 4i, so it moves out twice as far. Okay, so if you're doing these and you're getting a little bit confused by what's happening, make up a complex number for yourself, Z1, okay, and play with whatever they're telling you to do with it. And see if in the context of a diagram, then you can figure out where is it. Okay, so that's your dilations. Okay, so to explain, these two here are a dilation. Okay, one of them is Z1 and the other one has to be Z3. Okay, they're on the same path. One has just moved in closer to the origin. Okay, and then the last one that I want to talk about is this one here, okay? And it's the parallelogram one, okay? So you can always form a parallelogram with the origin. I'm just trying to see it now. There's one, for example. Can you see that? There's a parallelogram with the origin, okay? Is there any other one? No, I think that's the only one. So forming a parallelogram, do you know what? I'll draw it in so you can see it, if that's all right, because then I can explain it better. Okay, so forming a parallelogram with the origin means that the point across from the origin, so this one here, is the sum of the other two parts. I'm taking that from here, okay? So in other words, Z4 is up there. So that point that's across from the origin is the sum of these 2 points. Okay, so I hope that makes sense. So if that's Z4 in this case, it's made up of Z2 or Z3 and Z2, or of course he could be Z2 and he could be Z3. I'm not too sure yet. But I know from this one that if that is Z4 up there, one of these has to be Z2 and the other has to be Z3. Okay, and that more or less covers the geometrical properties of complex numbers in this one question, okay? So it's an important old question because, as you can see, there's no numbers at all in it and you have got to figure out who's who. Okay, so the first thing I do when I'm faced with this question is the following, okay? And it's a little bit hard for me to do because I'm digital, but I would draw in a line up here, a lot lighter than that in pen, okay? And then using my triangle, I don't know the right number for it, from my mat set, I would draw a 90-degree angle to that. Okay, or of course you can use a protractor. Okay, why am I doing that? I'm trying to figure out the 90-degree anti-clockwise rotation. Okay, so this point here is a 90-degree rotation from which point? So someone pop on the mic. Is that one a 90-degree rotation from this one? I'm going to name 1, or this one 2. Anyone hazard a guess?
2.
It has to be 2, correct. Okay, because if it was this one, then you would find your new complex number, the one that when you multiply it out, down much closer. Okay, so I would hazard a guess now, so that this is Z2 is equal to I times Z1. So he must be Z2 out there, and he must be Z1. Okay, going by him. Okay, and then it doesn't really matter which of the next two you do. Maybe this one, Z3 is equal to K times Z1. Well, from that one, we knew one of these was Z1. We knew the other one has to be Z3. Okay, and then from the parallelogram one, I probably would on my exam paper draw in my parallelogram as such, something like that, that doesn't clutter it, but that is your Z4 up there, okay? And you can see Z4 is Z2 plus Z3. Okay, so it does all link together, and if you know all of that, then you have this question fairly well covered. Okay, so identify which number is which by labeling the points on the diagram. Write down an approximate value of K. So let's go back. Z3 was K times Z1, okay? Well, you've moved in further, so K must be less than 1, and it looks like you're about halfway. So I would hazard a guess that K then is a half. Z3 is about half times Z1. Yeah, that feels right. If you've enjoyed this video, then why not join us in IT Sligo and use maths in practice. In conjunction with industry, we've designed an exciting new program in electronics and self-driving technologies, which uses cutting-edge techniques such as artificial intelligence, computer vision, and virtual and augmented reality. You'll need a H5 in maths to qualify. Check out the link below.